All right, it's time for day 15 of Advent of Code. Let's do it. Day 15, Beacon Exclusion Zone. You feel the ground rumble again as a distress signal leads you to a large network of subterranean tunnels. You don't have time to search them all, but you don't need to. Your pack contains a set of deployable sensors that you imagine were originally built to locate lost elves. The sensors aren't very powerful, but that's okay. Your handheld device indicates that you're close enough to the source of the distress signal to use them. You pull the emergency sensor system out of your pack, hit the big button on top, and the sensors zoom off down the tunnels. Once a sensor finds a spot it thinks will give a good reading, it attaches itself to a hard surface and begins monitoring for the nearest signal source beacon. Sensors and beacons always exist at integer coordinates. Each sensor knows its own position and can determine the position of a beacon precisely. However, sensors can only lock onto the one beacon closest to the sensor as measured by the Manhattan distance. There is never a tie where two beacons are the same distance to a sensor. That's good to know. Okay, it doesn't take long for the sensors to report back their positions and closest beacons. This is your puzzle input, for example. And then we have, 15-ish readings here, showing that the sensor is at x equals 2 and y, at 218, and its closest beacon that it detected is at minus 215, and so on and so on. Yep, that's what it says here too. So consider the sensor at 218. The closest beacon to it is at minus 215. For the sensor at 916, the closest beacon to it is at 1016. Drawing sensors as S and beacons as B, the above arrangement of sensors and beacons looks like this. Boom. This isn't necessarily a comprehensive map of all beacons in the area though, because each sensor only identifies its closest beacon. If a sensor detects a beacon, you know there are no other beacons that close or closer to that sensor. There could still be beacons that just happen to not be the closest beacon to any sensor. Consider the sensor at 87. That's the one we have right here, which is highlighted. Hope you can, maybe I can zoom in a little bit. Yeah. So the shiny one here. This sensor's closest beacon is at 210, so you know that there are no beacons that close or closer. So this is the sensor, this is the beacon, and this shows all the points that are within the same Manhattan distance as this beacon. If you, yeah, I will. So the Manhattan distance is, yeah, it's based on how you measure distances in Manhattan. How many blocks, because you have your streets and avenues, or the other way around. I can never remember. Anyway, so you have like a grid, and to go from one point to another involves going sideways a number of blocks and then going the other way a number of blocks, and that's what we call the Manhattan distance. So going 10 down or going 7 down and 3 to the left or 3 to the right, same distance. That's the Manhattan distance. Okay. Yeah, so the sensor's closest beacon is this one, and these pound signs mark all the points that are as close or closer to the beacon. So we know that there cannot be another beacon within this area, because then that's what this sensor would have picked up. So none of the detected beacons seem to be producing the distress signal, so you'll need to work out where the distress beacon is by working out where it isn't. For now, keep things simple by counting the positions where a beacon cannot possibly be along just a single row. So suppose you have an arrangement of beacons and sensors like in the example above, and just in the row where y equals 10, you'd like to count the number of positions a beacon cannot possibly exist. The coverage from all sensors near that row looks like this. So in this example, in the row where y equals 10, there are 26 positions where a beacon cannot be present. Consult the report from the sensors you just deployed. In the row where y equals 2 million, how many positions cannot contain a beacon? Yep, let's take a look. Okay, so part A, we load all the data. We define a regular pattern like this using a regular expression, and then we parse them all out and shove them into a list of, I call them pairs because there's a pair of a sensor and a beacon. So that's what a pair is. So what we have in there are 4 coordinates. Well, no, 2 coordinate sets, I guess. So the sensor X and sensor Y and the beacon X and the beacon Y. Okay. And once again, we create a set to keep track of what columns have, what columns we have left, or, yeah. So we go through all the pairs. We calculate the distance between the Manhattan distance between the sensor and the beacon, and that gives us a radius. So at this given row, if the row we're looking at is in the let's use the example. I can point and explain. So in this example, if this is what we're looking at, and we want to look at the row with y equals 10. So if we just go straight down from here, then we've moved 1, 2, 3 spots. And because we know that the distance to the beacon was, whatever it is, we subtract, the 3 that we've already moved, and then we know that we can move a number of spaces to either side. So that's what we do here. We, so we just go from like the sensor X minus the radius to sensor X plus the radius, and add those to the columns, and then finally return the length of the columns. And yep, for me that was what is that, about 4 million? Yep, that one was relatively straightforward. I got my best position so far, 500 and something, I think. Okay, that was part 1. Part 2, oh my goodness. Okay, your handheld device indicates that the distress signal is coming from a beacon nearby. The distress beacon is not detected by any sensor, but the distress beacon must have X and Y coordinates, each no lower than 0 and no larger than 4 million. To isolate the distress beacon signal, you need to determine its tuning frequency, which can be found by multiplying its X coordinate by 4 million and then adding its Y coordinate. In the example above, the search space is smaller. Instead, the X and Y coordinates can be at most 20. With this reduced search area, there's only a single position that could have a beacon. X equals 14 and Y equals 11. The tuning frequency for this distress beacon is 56,011,011. Find the only possible position for the distress beacon. What is its tuning frequency? Man, this was fun. It was hard, but it was fun. So he did this thing again where the solution to the first part is very prescriptive, right? So it says, okay, we're looking at a single line at a time, and we're doing all these calculations and so on and so on. And then the trick is, if you try to use that same method to solve number 2, it's not going to work, because you have the map is enormous. I think it's like, what was it, 4 million by 4 million, and having to do all of this for each of them is not something you want to wait up for. Let's just put it like that. So I had a lot of, I don't even remember what I did last night, to actually solve it. I had a yeah, I came up with a solution last night that worked. It wasn't very fast, as I recall. And then I spent a lot of time today trying to find a better way. Um, like, I mean, check this out. Like, there's all this, and this is like I've wiped all this out and redone it like at least 3 times. Trying to look at it and come up with some idea about what's the trick here? What's the insight I'm missing? And yeah, I went a lot of different routes. I was thinking um, something about finding these are, I mean, they're not quite circles, but and if we define our space as uh, distance is equal to Manhattan distance, then what we're looking at is effectively a circle. It has a center and it has a radius, and yeah. So I figured there might be a way to find overlaps and whatever, but that's not exactly what we need to do. We need to find things that aren't uh, covered by any of these. And yeah, I tried a lot of different things. This one approach took me the longest by far. So I have yeah, so I basically create a completely separate coordinate system. So instead of the coordinates being I don't need this here. Controller. Nope, there it is. You don't want to see that. Okay. Oh, I should. Like that. Yeah. Sorry, this is a little awkward. Uh, so is that the right way around for you? Yeah. Yep. Looks about right. Cool. Okay. Yeah. So the way that it's defined in the that's dead. Okay. So we have our coordinate system. So whereas the normal coordinate system goes like this 0, 1, 2, 3, 4, 5, where obviously, like, say, this one is 4.2. Yeah, you get the idea. You know what a coordinate system works, how it works. So I thought maybe the trick would be to come up with that's the camp. Maybe the trick was to come up with something where I could kind of transpose it so that I would, instead of having these kind of jagged rhombuses, I I would end up with squares. So I had a coordinate system that kind of rotated the whole thing a little bit. So the way that I did that was uh, instead of my x and y, I created like a coordinate p, which was x plus y, and a coordinate q, that's x minus y. That's not a y. X minus y. So this one right here becomes still 0.0, This one is 1.1, 2.2, 3.3, etc. This one here is 1 point minus 1, 2 point minus 2. This one here is 2.0. So yeah, all these ones down this way are like 0 as the second coordinate. I don't know if it would have been easier if I swapped them. Probably not. And then, yeah, so what you end up with is, so each of these rhombuses, so suppose we had a sensor here at what is normally called 3 point. Ha! On camera and everything. That's a 1. This is a 2. This is a 3. And this is a 4. Excellent. Okay. So suppose we had a sensor here and had the beacon right next to it. We would have these points, or only these squares. They would be accounted for, right? They were already be in use, so we can't use those. The beacon can't be there. Yeah, that's better. So instead of having the corners be at like 2.3 and 4.3 and 3 point, you can barely even see it over there. Gotta get out of the way. Yeah, so we have what, 3.2 at the top, and we have 2.3 at the side, 3.4 over here, and 4.3. I mean, that felt really awkward, and I thought there would be some really cool tricks in having like a coordinate system where this would effectively be a square. So we would have this corner would be so in terms of PQ, this point here would be 5.1. This point here would be no, this point here 2. That would be also be 5 plus 5 minus 1. This one down here would be 7 point minus 1, and this would be 7 point 1. Right, so these are. Am I in the way? Yeah. Other side. Here we go. Yeah, that works. Great. So you can see these are, if these were in a Cartesian coordinate system, so like a regular one that we know from math, you can see that these would be 4 points that are like at 7 corner, corner. That would be here. And that's a heck of a lot easier if you're trying to go through like the whole coordinate system, just like, yeah, top to bottom, right? And trying to find Yeah. So the point is the map is huge, like 4 million by 4 million. It's not feasible to just go through each one of them and go through each uh, each of those rhombuses and determine if it covers it for every single one. It's not going to work. So I wanted to find a way to be able to skip over stuff. So I knew that if I'm scanning like top to bottom and just keep going, I know that as soon as I hit like a corner here, I can, instead of just moving over one, I can check how wide is this, and then jump to the end of it, and then continue from there. And certainly that helped. Absolutely. I mean, this works. It just takes a lot longer than I am talking about the code, but I am not showing you the code. This one? Yeah. Yeah, that's the one. Cool. So yeah, that's this whole thing. It didn't take as long. No, it took way longer than I really wanted it to be. Wanted it to take. Usually these, once you get the right solution, it's like it's like that fast. Haven't quite gotten there with this one. But I'm pretty happy with what I ended up with. All of this down here, all this nonsense, turns out to be unnecessary. So what I'm doing instead is, so all of this is just like part A. Then I have a function called isCovered. So it takes it takes a couple of coordinates, regular XY coordinates, not the PQ nonsense that we were doing, and pass in the pairs of sensors and beacons. Go through each of them and check if the distance from the sensor to this point is shorter than the distance to the beacon that it sees. And if it finds a hit, then it returns true. Otherwise, it eventually returns false. Great. And then the trick that I realized, and I don't know if it's still taking longer than I really wanted to, but it's a reasonable amount of time. So I came up with this follow edge function. So it takes in a pair. And again, a pair is a sensor and a beacon coordinates. So you pass in those coordinates. It calculates the distance, and then we start by taking the sensor x coordinate minus the distance, and then minus one more, and that puts us right beyond the edge of. Let's take a look here. So in the case of this whole rhombus here, right? We know that the distance from S to B here is, was it 10 or something? So we move over 10, that would have put us there, and then we subtract one more. That puts us just beyond this area here. And the thing is, we have this whole gigantic map, and there's only one spot that is available. So it stands to reason that that particular spot is right next to one of the rhombuses, right? It has to be adjacent to one of them. Otherwise, there would be more than one, right? So, yeah, that's what I'm doing instead. So I have this follow edge thing. So go all the way to the left, and then we go down and to the right. And if you don't know how Python generators work, basically, you can call follow edge, and then you can iterate through it, through the return value, and whatever you yield, becomes one element that gets returned one at a time as you go through it. So this is how you make generators in Python. So that's what we do first. We go down and to the right. So as long as x is less than the sensor x, so we're going down until we're at that same level where the sensor is, at the same x coordinate the sensor is, and that's when we want to start going up and then back again, right? So that's what we're doing here. We go down and to the right, and then up and to the right, up and to the left, and down and to the left, and then we should end up back where we started. Otherwise we messed up, and I'm so glad I put this in because I had a tiny little mistake here. So assertions, they're great. Yep. So I follow the edge along all the different pairs, and I check if it is within the boundaries of the of the map. So you remember that in the smaller example, we assumed that they were at most 20. The coordinates were at most 20. But in the bigger one, we know that they have to be between 0 and 4 million. So, yep, check that it's within bounds and that it is not covered. And if it's not covered, then we return the value and we're actually done. And how long does it take? Oh, 10 seconds, it says right there. It's way longer than I really wanted it to take. I'm surprised by this. Some of these rhombuses must be enormous since it takes so long to go all the way around them. But yeah, once again, one of the tricks that you can use to figure out how to solve these problems is when something looks like it's becoming computationally infeasible, like it's going to take too long, or it's just too, the complexity is just too much, right? A lot of the time, especially when it's, sometimes when you're solving real world problems, there isn't always like a clever way you can do stuff. But with these puzzles, we usually know that there's a way to get an answer pretty quickly, and that always helps to know that there is one. So if you're looking at a problem and it looks like it's becoming computationally, extreme in some capacity, in some way, processing, space, whatever, it really helps with these puzzles to try to think about what are some things that are that there are fewer of. What is, if you can flip your for loops inside out or something, so that you have so that you may still have a time complexity that is n squared, whatever, right? But instead of n being 4 million, n might be how many pairs there are instead, right? And that's a number that's much more palatable to try to work with. And yeah, but this was fun. I actually a couple of times looking at other maps, thought about, oh, what about creating my own coordinate system? And yeah, so that's tried it out, and it didn't really help much. There was a lot of funny little insights there too. You can see I have them sticks out outside of that, the top, because you know that because when I'm going through, if I'm going through this, according to the diagonal sort of coordinate system, I'll be starting here, and then going like taking these and taking these and taking these and so on and so on. And that means that if I ever meet like one of these rhombuses, I know that I'll be able to skip over like however wide this is. Or I mean, this could be a huge square if you look at it, you know, turn 45 degrees. So I can always skip over those. And that helped a lot, you know, that made it, you know, quite a bit more reasonable to try to work out. But then I realized that, you know, some of these, I mean, we're dealing with a 4 million by 4 million map, right? And the input was, is that it? Yeah. Let's look at my input. There's 32 of them, right? So if 32 of them cover a 4 million by 4 million map, I feel like there's a pretty good chance that some of them are going to be enormous, right? And I realized that if I come across, you know, when I go through like here and then I go there, and then when I get to the end, I start over, increment like my P, and then da, 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 da. But if I'm here, and then I jump to the next one here, and this one is blocked, then if that means that I have one of these squares that goes, you know, at least to there, but very likely further down, right? And so if it goes further down and it goes all the way up here, I have a little trick. That's the yeah. It didn't work anyway, so I'm not going to show you. It doesn't matter. But if it sticks out, that means that not only can I skip from here to here, if this is a big enough rhombus, I might be able to skip from here and like way down. I mean, we're talking about 4 million by 4 million. This is just 5 by 5, right? I mean, there's a good chance that some of this is just going to be covered by in like one or like a few enormous rhombuses. So I wanted to, if I get here and then I see one of the areas, then yeah, I'd be able to not just skip over in the Q direction, but also in the P direction. But yeah, it was a hassle. It was a dead end. But I tried it out. It was fun, and here we are. Yeah. So I'm really curious how other people solve this. I kind of feel like that there's some extra insight somewhere that some extra insights that I've overlooked that would have made this more tractable. But it works, and it was fun. So yeah, I hope this explanation was useful. If you have any question or comments, you can leave them below, and I'd be happy to answer them. Otherwise, just like and subscribe, and I will see you tomorrow. Right. Bye.